All right. We are excited today to have Andrew Cherry joining us to talk about Freya, which is an implementation of Web Machine, an HTTP state machine web framework, an actual, web stack that he and I have been working on. Andrew is a developer at Zincro. He's been working with .NET since 1.0, but always wanted to be able to use the fun bits from Haskell, Erlang, etc. commercially. F# brought back the fun to .NET, and now he works helping people apply functional practices to build better software. Recently, he's been working on a stack to make F# feel like a warm and fuzzy way of writing software for the web. And so I'm going to hand it on over to Andrew to get started. Thank you, Andrew, for joining us today, and we look forward to what you have to show us.
That's great. Thanks, Ryan. Hopefully you can hear me.
Yes, I can. Sounds good.
Fantastic. All right. Well, this is a slightly abbreviated version of a talk and workshop I actually gave last week at LambdaConf in Boulder. Just as a brief aside, if there are any sort of F# people that happen to be around that part of the world, then I definitely recommend that LambdaConf 2016 is definitely something worth going to. It'd be great to see more F# people there. So I gave this talk and workshop. It was at least 2 hours there. I'm not going to talk for 2 hours today, so I'll try and cut this down a little bit. So, as Ryan said, Freya is a web stack that he and I have been working on going on for a year now, I guess. It came out of a few sort of personal projects which both he and I had. We combined some of the ideas from those and sort of try to avoid sort of splintering things too much. So Freya is more of a stack than a framework in some ways. It sits on top of the OWIN standard, which is an open standard within the .NET world for sort of talking between sort of web servers and web frameworks or abstractions over web servers. And it really came out of a desire to do slightly more accurate web programming and to give a few different options, as I was rather dissatisfied with at least what we had in the F# world. So obviously sort of web API and that kind of thing work quite well, but they're not as functional as I might like to see them. And it's always interesting to have some more options when we start talking about sort of frameworks and stacks in different spaces. I felt that the web space in F# could definitely stand some more options. So this is just a very quick sort of skim through the sort of workshop that I gave last week. We'll go through a sort of quick first half, which is just looking at sort of how Freya works at the sort of basic level, the sort of essentials of the programming model, and then we'll do a quick worked example, which is implementing the to-do backend sort of API, which is a sort of standard community-driven kind of project for comparing different implementations of backend software. Obviously, sort of each half of this was at least an hour last time, but I'm going to skip the fact that obviously there were exercises and that kind of thing. We'll go straight to results. Just to sort of show, before I do sort of dive into that, just to show you what you can actually expect to see by the end of this. This is our sort of final implementation of the to-do backend side of things. I'll skip over some of the nastier code at the top, but this is the kind of thing which you'll be seeing later on. So this is kind of what Freya looks like. Sort of various functions like this, you'll see this kind of Freya computation expression around a lot, and this kind of declarative way of defining state machines and sort of machine-style programming. But I'll talk a little bit more about what that means later on, and then we'll dive through and actually sort of build this up from scratch. So just to convince you all that this does actually work, we'll just see this actually run to start with. So this is what we're hoping to get to. I've spun this up on localhost 8080 and we actually pass all our tests. I'll go back to failing them all soon. So just as a quick sort of introduction to Freya, as I say, there are various levels of abstraction which are available in Freya. There's this sort of Freya core abstraction, which is quite a low-level way of working with, if you like, the sort of the nuts and bolts of sort of HTTP requests and responses, and actually working with those directly. And then there are higher levels of abstraction which are, a little bit further away from that and sort of start to provide some slightly more sort of logically oriented approach to actually building up sort of web responses. As I said earlier, we build on the OWIN standard, which, if you're not familiar with OWIN, it's just a fairly basic standard and a specification for how web servers should expose their functionality to web frameworks and vice versa, so that if you write a web framework which it complies with the OWIN specification, you should be able to run that on any web server. That means things like Katana, it means things like IIS, it means it's easy to host those kinds of things on Azure and potentially other web servers as well, provided they implement this standard. It's quite a simple standard. I'm not going to go through the exercises which we did on it previously, but just to say that the basic OWIN interface is this func idea. So your web framework at a fairly fundamental level just needs to be able to handle and implement this func, which takes an iDictionary, which is essentially your state, your HTTP request and your response data, and returns a task so that the web framework or the web server knows when you're done, basically. It's a cross-language and cross.NET standard, so it's based on mutation, and this mutation dictionary of state. But we try and hide a little bit of that in Freya. Just to look, though, one of the interesting things to see first off is that if we want to work with OWIN from pure.NET, we can actually do that without using Freya at all, and it would look something like this. So if I were to say, I'm going to use my Katana web server here, which is just the open source Microsoft implementation, which supports OWIN, and I'm just going to literally create this function from scratch, which is just an iDictionary, a string to opt, and implement this signature, which OWIN requires me to do. And I'm just going to modify that dictionary in place and set various things on that. So I'm going to say that the response status code is a 200 and give that kind of thing. And I'm going to modify the body, which is just a stream. If I actually do that, I should be able to spin this up and see that this actually works. So if I go in here and hit this, I should be able to see that if I just hit localhost 8080, I just get a hello world. It's not a particularly nice programming model, but it is possible to work with this kind of raw OWIN abstraction just using F# quite simply. But that's not really what we want to be doing, so we've got Freya Core, which is providing our lowest level abstraction over this and giving you a computation expression for working with that underlying OWIN dictionary. So it takes that OWIN environment, wraps it up into a computation expression, and gives you some functions you can use to work within that computation expression. So in this case, what that tends to look like is something like this. Now, this is still fairly ugly. We're actually just working with that underlying state directly, rather than using any of our nicer typed abstractions, which we'll see in a moment. But we'll see that rather than actually having to implement this func with a dictionary and a task, we can just use our Freya computation expression. And then rather than giving the hello world function to our server directly, we'll use this OWIN app func module and a Freya method just to turn that into the interface and the func that our server expects. So all that OWIN app func and Freya is doing is just taking our computation expression and turning that into that func iDictionary. But that's still pretty ugly. We're actually still having to work with that environment directly and modify that dictionary. It's just that now we're doing it in our Freya state. So let's move on and actually see that we can make that slightly nicer. We don't really want to work with that dictionary directly. What we'd really like to do is actually use a type system rather than just throwing strings around all over the place. What we'd like to do is work with that complex data structure in a more safe and more effective way. So the way that Freya does that is using lenses. If you're not familiar with lenses and you're not familiar with what a lens is in a functional sense, a simple analogy would be to say that a lens lets you focus in on a small subpart of a larger structure. So if I've got a big complex data structure, in this case our state object, which has a big dictionary, which has nested dictionaries and all that kind of thing within it, then a lens can let us work with just a subpart of that structure. So what we can also do with lenses is we can convert the data types there. So we can actually write something which lets us see that subpart of the data structure as something else. As long as we provide essentially a function which is a to and from converter, we can just see that in whatever type we want. So Freya actually integrates the ether lens library, which I have to admit to having written as well. It's a pretty simple library. It's a single F# file in its implementation, and it just lets us use lenses over F# and sort of general .NET data structures. So what does it actually look like in terms of its usage within Freya? Well, it would look something like this. So if we now have a look at our hello world function, we'll see that it's a bit different. We're sort of no longer actually working with the dictionary directly. We're using these Freya functions here. And a lot of the functions you'll find that you use on a regular basis are in this Freya module. So whenever you're sort of working with the HTTP state, you'll probably find yourself using things like setLens partial, getLens, which are simply functions that will say, right, okay, given a lens to a particular thing, I want to work with that. In this case, this response.status code is actually our lens, which is a lens to the status code, and our reason phrase is, as you'd probably guess, a lens to the reason phrase. But you'll see that what's kind of interesting here is that they're actually typed. So if you can actually see the sort of very small tooltip which might be popping up there, you can see that that's a lens from Freya state to string. This one here is a lens from Freya state to int. And it means that the data that we're actually working with now and the way that we have to work with that is actually strongly typed. If we were to look at something else which has a slightly more complex type signature, look at another aspect of our response, so perhaps something in the headers. If we were to say that we want to set the age header, we could do that using this, but what would it actually expect in terms of the data? Well, if I just try something like I want to set the age to 45, it's going to complain about that because it's actually expecting an age type, not an int. So we actually have a type system which embodies quite a lot of the HTTP standard in a strongly typed way. So I have to provide proper typed data to all of these things, even though the underlying data structure is just a big dictionary of strings. If I actually write this response headers.age, it'll actually be converting this to the string representation of my header under the hood and writing that into the dictionary. So we've already found a slightly better approach to doing this. We've got a strongly typed view of a loosely typed data structure. As you can see, we've got these lens functions, and you'll note that they're actually partial lens functions. So when we have our lenses here, they're either total or partial lenses, and basically what that means is they either are or aren't guaranteed to give back some data. So a partial lens is a lens which might return some data because that data may or may not exist within the data structure. In this case, the OWIN standard actually says that the status code doesn't have to exist in the response. If it doesn't, the server is just going to assume that it's a 200 or something similar. So we have a partial lens here. There are some things, if we wanted to work with the data which we do know exists within the request or the response, we actually use a total lens to that. So if we would say, right, let's take a property, the request, which must exist. The request must have a path, I believe. And that's probably going to ask me for a string, or something similar perhaps. And you can see that obviously now we've got this set lens rather than set lens partial. So whenever you're using lenses in Freya, you'll find that you're either using set or get lens partial, or just this set lens. And actually the request itself and the lens that you're using will tell you that. You won't be able to compile this if you're using the wrong type. It will give you a sensible error. So we've got a slightly nicer approach to working now. We've got this strongly typed access to our state, and that's cool. So we can see that in our little example here, if I just remove this kind of stuff, we are setting up. We're writing this hello world, and we're doing it in quite a strongly typed way. So the next thing to do is to sort of note that that's great, but it's not very useful. As at the moment, we're kind of assuming that all of our applications only have one resource or one root, which is probably not going to be the case. So the next thing that Freya provides outside of that core abstraction is the concept of a pipeline and the concept of a router. So there's a very simple abstraction that we have, which is a Freya pipeline, and that's simply a Freya function, which is one of these functions, that returns a specific type of value, in this case Freya pipeline choice. And Freya pipeline choice is just a very simple union type or sum type, which is either next or halt. And all that means is that if I say at the end of here, then this function, the signature is now Freya pipeline choice. And that means that this is a Freya pipeline function, and we can actually compose those and use those in slightly more interesting ways. And we might see a little bit of that later on if we have time to look at it. But one of the things to note is that quite a lot of the abstractions and the tools available in Freya expect you to be using pipeline functions. So for example, the router that we're about to see actually expects that the functions that you're routing to are pipeline functions, not just sort of some generic function. So what we have now is, if we move on a little bit, you'll see that I've duplicated my hello world function, and I've created a new goodbye world function as well, which has the obvious difference, and I've introduced this new Freya router, which I've called converse world in this point. And what you'll be able to see is that we have two roots in our router, and again, we have a computation expression syntax for setting up routing. It's strongly typed. It uses these URI templates, which we'll talk about in just a moment. And you'll see that I've said that the /hello path wants to go to my hello world function, and unsurprisingly goodbye to my goodbye world function. And then you'll note that those are Freya pipelines. If I was not actually returning this this value of sort of next or halt, you'll note that this actually complains. So Freya router always expects me to wire things up to a pipeline function. And the reason for this is that pipelines are essentially our sort of macro form of composability. So where we have this this Freya router, and I'll just go back and add that in so it still compiles, you'll notice that we're calling Freya router to pipeline at the end of this computation expression. And what that actually does is it turns this router itself into another pipeline function, so a function that returns next or halt. And the way it does that is to say that, okay, if the router manages to match any of these paths, it's going to invoke this function, and then it's going to return the value of that function. So these need to be pipeline functions, so this whole thing can be a pipeline. And you might be wondering what happens if it doesn't match any of these routes. Well, in that case, it will just skip straight through the router, and the router will return next. In this way, you can actually build up sort of chains of routers, pipelines of multiple routers, so you can compose your application out of smaller chunks. And if you're wondering why we return next or halt, we have a simple way of composing pipelines which says that you may want to stop the execution at a certain point if that pipeline component returned a halt. So this lets you do things like create functions which might stop the execution of your request at an early stage if, for example, the request didn't have adequate security clearance or headers or something like that, or if you detected something. We wanted to essentially stop processing that request at an early stage. You can actually do that by creating a pipeline which may or may not halt at certain points. There'll be some interesting docs on that in the website quite soon. But for now, we might look at that more a little bit later. But for now, just assume that most of the things you're going to want to work with are actually pipelines. And it's very easy to turn any function into a pipeline just by returning one of these values. So in this case, I'm actually returning it using the computation expression syntax, but I could just return next as a simple case for that union type. So just to spin this up and run it, make sure this actually works. Just so that people are aware that I'm not just making this up as I go along. We'll now see that if we go to the hello path, we get a hello world. If we go to goodbye, we will hopefully get goodbye world. So that's actually running through my router and matching things properly. If I now go there, I just get an empty request. The reason for that is that the OWIN server is still running, and I've just returned without ever matching anything. So I never invoke anything to write to our response. So we just get the default response, which is just empty. So I've never written to the body. I've never written any headers. So it's just going to be whatever the server thinks is a good start. In this case, it's just an empty 200 OK. All right, so now we've got a way to see multiple resources at multiple places. We know roughly how we can match on those. One last thing to talk about with our router is that we use URI templates. So in keeping with our sort of goal for Freya, which is about working as closely with the HTTP standards as we can, we use existing standards. In this case, the URI template standard, wherever possible within our framework. So a URI template is essentially just a standardized and sort of specified way of defining what a path could be and how it's constructed. So, for example, a path might be just a literal string, or it might have elements within it which are going to be replaced by particular bits of data or lists of data. And it has a fairly obvious syntax, which actually looks a lot like most routing frameworks, but it's actually based on sort of open web standards. There's an RFC for these, and we implement that in Freya. URI templates have a useful kind of property, which is that obviously you can match against them, and you can also populate them. So you should get a round trip between a URI template and the data it contains. And then rewriting or re-rendering that URI template with some data. So we can actually use those URI templates in later places, and especially when we start to talk about hypermedia at points in the future, URI templates become a very useful thing for defining the relationships between our resources. One last thing with this router is you'll notice I've got this all keyword at the start. And that's basically saying that this return responds to all HTTP methods and to all verbs. In this case, that's probably what I want. I don't really worry too much about what we're actually responding to here. But if you actually wanted to respond to something which was, let's say, only GET requests, you could, I think, do something like this. And that would give you a route which only responded to the GET method, which means that even if you hit the /hello path, if the verb is not GET, then you will simply fall through and that route won't be matched. You can obviously have multiple methods in there as well if you want them. So if we were to say, right, this wants to respond to GET and head, for example. Notice that I'm using these sort of strongly typed sort of method properties. These are just the standard sort of union case properties of our method type, which again comes from some of the Freya libraries. And at this point, I should probably mention Freya types. So we have a set of type libraries which implement most of the HTTP RFCs, again providing a strongly typed representation of all of the things like HTTP concepts, such as verbs, paths, parsing, URIs, language tags, all of that kind of thing is part of our type system. And you'll notice up here that we've actually got freya.types.http open, which is where this method type is coming from. We try and reuse that kind of data and that sort of type system everywhere sort of within our framework, so that we can write sort of new additions to it and have them work well as part of the stack. Again, you'll notice that things like our URI template is up here as part of our open modules. That's another part of our stack. We've got probably 5 or 6 type libraries as part of Freya now, which implement different logical groups of RFCs. So let's carry on with looking at where we're at. One of the nasty things that obviously we can already see happening in this implementation is that I did some horrible copy and paste, and I basically have 2 functions here which look extremely similar. That's probably not something which we'd ever really want to see in a real-world app. So if we look at what I've done next, we can see that we can actually refactor in a Freya world. And obviously, because these Freya functions are essentially just normal F# functions, we can write some new ones and then call them within other computation expressions, and we can parameterize them. So I've pulled the logic of writing this message and these standard headers out, and then I've just sort of referred to that function. I've used that function within my actual hello world and goodbye world functions that I had before. So you can start to see a way that we can actually get some reuse out of these things. If I wanted to break this down into smaller chunks and start to create reusable things for my application, then I can start to do so in a very simple way just by composing these Freya functions. So the last sort of little bit to look at when we start to look at the building blocks of a Freya application, and this is the low-level parts of Freya, is how to actually start using the data which comes through in an HTTP request or an HTTP response, where that data is dynamic. So obviously up until now we have our roots which we're matching on things like hello and goodbye, but what if we actually want to take some dynamic data out of these things? So again, we've got some lenses here which can help us. So if we change one of our roots to include some dynamic data, so if we changed, for example, to have a root which looks something like this user's ID, and we'll note that that ID is the syntax for some dynamic data which needs to be matched in that root, we can actually start to say, right, that the data which was matched as part of ID is now going to be available as part of our environment. And we can use some lenses to go and grab that data out. In this case, that's going to look something like this. So what I've done here is I've changed my roots to actually take a name part of the path, and then changed my functions to actually go and get the value that was matched as part of name. So you'll notice that we're back to using our lenses again, so we're going to grab the name property using this getLens partial. But instead of using the request and the response modules, which contain lenses which are relevant to the request and the response, we use this root module, which unsurprisingly contains lenses which are relevant to data matched as part of the root. You'll notice that this is called atom, so we actually take the terms here from the RFC for URI templates. So there are different types of data which you can match and also put into URI templates. Essentially, sort of atomic strings or atoms, lists or lists of pairs. In this case, we're just expecting to get a single string out of this, so we just use this root.atomLens and give it the name of the data that we're expecting to get out. We'll find when we do that what we get back is this name value, which is the string option, and it's a string option because we've got this partial lens. So I do something a little bit unpleasant here, which is actually refer directly to the value of the option. Obviously, if that option was none, I'd get a charming runtime exception at this point. But I don't actually need to worry about that really in this case, because I know that if I didn't match a path, in this case hello name, which contained that root data, then this function is never going to be invoked anyway. So I can actually take a little bit of a nasty shortcut and I can refer directly to that option's value If you wanted to be a little bit nicer about this, then obviously you could pattern match over this or provide and use a function which says, okay, basically give me the value of this or a default in a safe way. There are probably sort of functions a lot like that knocking around in libraries like F#X. But in this case, I'm not too fussed. I'm pretty confident that although that's theoretically possible to get a runtime exception, I'm never actually going to hit it. And sometimes we do make a few assumptions like that in Freya where, yes, the type system can't prove to us that this is safe, but we logically know it will be. All right, so that's actually sort of given us all of the building blocks that we need to actually be able to build a Freya app, at least a fairly low-level Freya app. And we'll start to look at a higher-level abstraction, which is our machine-style framework in a moment. Before we do that, though, one thing which I will just note, and I know this is a little bit sort of controversial within different parts of the F# community, we do provide two types of syntax. So wherever we see these Freya functions, obviously we're using the sort of more verbose computation expression syntax. We're using these sort of fully qualified functions, named functions rather than operators or anything like that. But you can actually sort of say, right, well, I would rather use a more concise operator-based syntax. What that would look like in this case might be something like this, so that you'll see that our Freya functions become a little bit more simple in some ways. I'm not suggesting that you always want to do this. If you are familiar with sort of languages which are a bit more operator heavy, you might prefer this kind of style. You'll see I've even given an example up here of where we're using an operator for a set length partial. There are actually operator-based alternatives to most of the things that we do, but you don't need to use them. So in this case, I've taken a fairly concise approach to this using these, and I'm sorry to use the M word, but monadic operators. If you like this kind of thing, just be aware that it's there as an option for you. If you don't, you can happily forget all about it now in the knowledge that you'll never actually need to use that. Everything that you want to do can always be done using the more sort of F#-like syntax of these computation expressions. All right, so we've got some data out. I'm not going to bother actually proving to you that that works. You might just have to take my word for it. Obviously, I'm using my slides from last week. We're not going to have a break in the Q&A at this point unless people do have obvious questions. If people have been asking questions and they want to ask them now, Ryan might jump in with them. If not, we'll just skip straight into our worked example and we'll work out how to actually build an API using the next level up in Freya, which is a web machine.
I don't see any questions so far, so you can go ahead and continue on. This is excellent. Thanks, Andrew.
No worries. All right then. Well, we can always, if there's any Q&A at the end, I'm sure we can handle that then. So I've talked about Freya as being a stack, and essentially what I mean by that is that the libraries within Freya are really designed to be used in a sort of fairly pick and mix style. If you just want to work with OWIN requests and responses in a strongly typed way and just use that kind of router logic, then you could just use only the stuff we've seen so far and that will work perfectly well for you. But what we're trying to do is to create more useful abstractions. So working directly with HTTP requests and responses is perhaps a little lower level than we often actually want to be. So we're usually more concerned with the logical handling of these things. And it would probably be more useful to us if we could actually just start to describe our resources in a more declarative way, rather than actually having to go to the nuts and bolts of working out what all of the potential cases we need to handle might be. So Freya Machine is the part of Freya which does this. And it's what we call a web machine style framework. What happens here, and this is an idea taken from work, I think sort of originally in the Erlang community with the original web machine framework, and certainly from some other language communities as well who've got similar concepts, is that we represent the processing of an HTTP request as a decision graph. So at each sort of step in that decision graph or tree, which you could look at as a state machine, we're asking a question about our resource, and then we're taking sort of what a branch or a path in that tree to decide what the next option might be. So as an example, we might be at some point in that tree asking a question which is, does this resource exist? And if the answer that comes back is, yes, it does, that's a true value, then we'll carry on processing how to return this resource. If the answer that comes back is actually false, then what we'll do is start working out how to return perhaps a 404 or some other piece of data or status which better represents what the response should be. So, for example, we might say, okay, right, well, it doesn't exist, but did it ever exist? If it did, then perhaps it was moved. If it was moved, was it moved permanently? And if that's the case, then we'll work out exactly which HTTP status code is the right one for this context. But all we actually need to do is provide answers to questions. So rather than us having to write the logic for that in our handlers, we can actually just allow the Freya machine to take responsibility for working out what that correct logic might be. It might sound like you're going to have to answer a lot of questions at that point, but one of the nice ways of working with this, and one of the nice aspects of machine-style frameworks, is that you don't actually need to answer all the questions. So each of the questions in that tree actually have a default answer. The default answer, for example, for does this resource exist is true. And if you know that's the case, then you never need to bother overriding that default answer. You only need to actually supply answers to the questions which you care about. So the Freya machine is, unsurprisingly, another computation expression which you can use. It's a slightly unusual computation expression. We've made very heavy use of customizations and custom operations within that computation expression to try and give a strongly typed but quite declarative syntax. There are some nice aspects to the machine model as well, especially the one in Freya, which goes a bit further than most of the other frameworks have done. There are some advanced topics around things like allowing you to actually extend the graph and modify the graph to provide your own logic for handling requests. We'll skip over that today, but that's definitely something which you might want to read up on when we actually get the documentation out for that. As much as anything, that's a great way for you to be able to handle sort of new scenarios which come up in the space of your app. So, for example, someone that wants to support something like a custom verb, sort of custom headers or custom logic based around combinations of those things, could actually extend that default HTTP graph to handle all kinds of new scenarios and to extend that logic. So let's have a quick look at the worked example. You saw earlier on that I was running these tests, which are part of todobackend.com, and that's basically asking me to implement an API for a very simple to-do list. So todobackend.com is essentially the back-end equivalent of the project which came first, which was comparing lots of different ways of implementing to-do lists in different front-end JavaScript frameworks. Someone came up with the idea that it might be useful to be able to compare the back-end implementations across frameworks too, and coincidentally it provides a really neat way and a very low-friction way of people being able to get up and running and see whether what they're writing is actually useful and whether they're meeting some specifications without having to start writing your own tests and frameworks and all that kind of thing. So we know from earlier that my final solution to that actually worked and passed that test, but let's actually start building that up now from scratch, as we might do if we wanted to actually build a real API. So let's have a look at what our stage 1 looks like. So a few things to note here. We're not going to worry at all about the implementation of our actual sort of back-end domain logic for to-dos. We'll just assume that we've already written that. One of the things to note, which is a nice thing here, is that we don't need to let our web API or our HTTP logic pollute our domain model. So our domain model over here, this to-do store, knows nothing about the web, fundamentally. The only thing that the types that are relevant to that have, which is slightly unusual, is that they know how to convert themselves to and from JSON. That's something which you may find handy. There are obviously lots of different approaches to serialization and that kind of thing. We've chosen one, which we'll see a bit later on here, but Freya doesn't actually impose any choices on you in terms of sort of data serialization frameworks or anything else. If you like things like Newtonsoft JSON, you can perfectly sort of plug that into the way that we use things here. So I'm going to start with stage one here, which is I'm going to have a Freya machine, and I'm going to use an HTTP graph within it. I haven't introduced Freya machine, but I think you can probably guess by now what that actually is. This is our computation expression for configuring resources. We haven't really done a great deal of configuration here. We've just said, yes, I want to use HTTP. And I've wired that resource, this to-dos resource, up to our router. You'll see that I'm using the resource keyword in our router here rather than the root keyword. All that basically means is that a resource is a root which accepts all verbs. And the reason for that is that we actually want to specify the verbs or the methods, if you like, that we handle as part of our machine and not as part of our router. It's useful to be able to do that on a per resource level. So we just say that, right, okay, we'll defer the handling of that kind of thing to our resource. So if we go ahead and we run this now, we're going to find that significantly less tests pass, which obviously is a good thing because we want to make sure that we're actually writing something here. Not such a great thing in terms of making us feel warm and fuzzy, but we can actually then start to develop what we're writing in response to the tests that are failing. So a little bit of a TDD-esque approach to this, I suppose. Alright, so let's try and work out how we make this first failing test pass. The API root responds to a GET, and cause headers are set up. Well, we haven't set any cause headers up at all. We haven't mentioned cause. We haven't written any configuration which would let us have cause. So let's go and work out what it might need to do that. So the changes I've made here essentially is to say, right, I've opened my cause module, which gives me the types that I'll need for cause, and again we have those as a strongly typed approach. I've written a few functions which let me know what headers and which origins are actually going to be acceptable here. So I'm going to say, right, I'm going to allow accept and content type to be cross-origin headers, and I'm going to allow my cross-origin requests to come from anywhere. And you'll notice I have this big long type, which is the allow origin range, which is actually a sort of direct representation of what that RFC or what that standard actually says. I'm also writing a function which lets me know which methods are going to be appropriate for this resource at this point. And then I've gone into my machine and I've started answering questions about what this machine can do. So the first thing I've changed is I've said that I'm using HTTP calls. What that's actually doing is it's extending the HTTP graph with the logic to handle calls. So it's added a few more decisions in there. It's added a little bit of extra logic so that it knows how to look for cause headers in the request and then work out whether it needs to send cause headers in the response. So I'm going to answer a few questions. I'm going to answer or configure a few things here. I'm going to say that the headers supported are my cause headers. The methods supported for cause are my to-do methods. And the origin supported is this cause origins. And I'm also going to go in here and I'm just going to say the general methods supported on the resource are, again, my to-dos methods. I'm just reusing that function in two places, which is why I actually have broken this out and made it a function rather than putting it inline in here. If I do that in one place, I can make sure that I never forget to update the other one. So that's cool. We have this this thing now. So hopefully, if I run stage 2, I should fail in a slightly different way. So let's fire that up and see which tests pass and which fail now. All right. Well, it still failed, but it failed in a slightly better way. It didn't complain about cause, it just complained about the fact that it didn't get the result that it wanted to have. It got a 406 back, not sort of some nice kind of 200 with perhaps some relevant data. So why did it get a 406 back, and what does a 406 mean? Well, as I know that we've all memorized the HTTP RFCs and that we've all got our HTTP status codes firmly committed to memories, we'll all remember that sort of not acceptable means that the content or resource representation that the client asked for wasn't one that we said we could actually support. So in this case, the client, the web browser, is actually asking for a response in JSON, and we haven't said that we can actually give it JSON. So when we go through and the machine tries to work out, can we handle this JSON type that it's asked for, the answer is no, because we haven't said we could. So we're going to need to add a little bit of extra configuration here. So we're going to add the media types that we support for this. And you'll see that again, I've just written this Freya function which returns a list of media types that we support, and in this case that media type is just JSON. Again, this media type is a strongly typed representation of a media type specification from the HTTP RFCs. This media type.json is just a shorthand for that. If you wanted to actually create your own media types, you can do that quite straightforwardly. You could actually just parse a string version of media type or anything like that using the type library. So what I've done here is I've said an extra bit of configuration, an extra property of my resource is that the media type supported is this value. So let's run that and see if we fail in new and exciting ways. Oh, we actually passed that one now. So we did send something back. We said that we could handle JSON, and that's great. So it's at least got past that content negotiation stage, and it sent a response back. It probably didn't send a very useful response back, but we'll deal with that later on. Let's try and pass the next test. So we are looking for this to handle a post. So we're going to need to tell our resource how to deal with a post. I'm going to just briefly take a quick break to factor out some of these things here, and we'll see that some of the common properties of all our resources I've pulled out into these common functions. And I've created a common Freya machine resource here, which includes things like this request for us to use HTTP in cause, and includes these common sort of cause headers and media types. And that's because whatever we're doing in our API, we know that these are going to be common across all of our resources. At the moment, we've only got one resource, this to-dos resource, but we know that these properties are always going to be common. So rather than having this information in each resource, we just now include the common resource. And that's just a simple way of composing Freya machines. So now that we've tidied that up a little bit, we can go and look at how we might support post. So what will I do here? So I'm going to start from the bottom and then we'll work up to see how we've done this. This is quite a big jump, this one. The first thing I do is say, right, okay, I'm going to support an extra verb on my to-dos. I'm going to support post. And then I'm going to need to write some functions to support this do post configuration. So this is a function which is going to be invoked whenever a post is handled. And so I've written this to-dos add do function. What that looks like is this. I'm simply calling this to-do add function. Now, we'll gloss over this to-do create for a moment, but what this is actually doing is reading the body data from the request and turning it into a to-do create type, or a to-do create option type specifically. And this is the function which my to-do store, or the type which my to-do store actually expects if I'm going to be adding a new to-do. So I read the body and I get one of those back, or at least I hope I do. Now again, in this case, like we did in our previous example, we can actually just take the value of that option because we know that this is only ever going to be called in a place where we expect that to be the case. We could actually sort of say that this is perhaps slightly less safe because we know that even though there's definitely going to be a body here, we don't necessarily know that what's in that body can actually be turned into a to-do create. We might talk a little bit later on about why that doesn't matter too much. What we're going to do though is we're going to run this to-do-store.add function with our to-do create. Now to-do-store.add is actually just an async function. It returns an async to-do. So in our Freya computation expression, we can use this Freya from async function to turn that async function into a Freya function, and then just let us call it as normal. So this function is actually going to take, use this to-do create, which we read from the request, and create a new to-do in our to-do store, and then return that to-do. So we can see that this is a Freya of to-do. One interesting thing at the end here is this call to Freya.memo. All this basically means is that we memoize this function. So the first time this function is invoked, we'll actually run this function. The next time we'll use the stored value from the last time we ran it, so that this function essentially only ever runs once. And that's actually once per request. That's quite a useful property, as well. We might see it a little bit later on. It means if we memorize something, doesn't matter how often we actually call it, we can always assume that it's safe to call multiple times, but the underlying logic in it is only ever going to be run once. So our to-do-add function actually doesn't want to return anything. This do post actually just wants a Freya function which returns unit. So in our to-do-add do function, we will just call to-do-add and then just throw the result away and return unit. All right, so now we should be able to see that if we run this, we will run our to-do-add function and see if we pass. Well, we don't, and there's a reason for that. The reason is that our post actually expected that it should respond with the to-do which was posted to it. So we actually need to return that to-do that we just created in our to-do store. And to do that, we're going to need to handle something else. So let's go and have a look about returning that. In this case, we need to say that we'll implement this handle created function. Now, handle created is the return handler for a situation where we've created a new resource. So after do post or potentially do put in certain circumstances, if we've created a new object or a new resource on our server, we will go down a path in our machine, which will mean we'll return this handle created. And what that's going to do is essentially a 201, 204, something along those lines. Yes, you'll note my haziness on that, as I can't remember it off the top of my head. But we're going to want to handle this thing here. We're going to want to override our handle created, which by default won't actually return any data. So we're going to write a function. We've already got our to-do-add do. Let's add to-do-add handle. And again, we call this to-do-add function here to get the to-do that we actually added. And you'll notice that theoretically here we would be calling our to-do-add function twice. We actually only want to add this to-do once, but we're safe here because we've memoized this function. So in this case, I'm going to get the to-do which was the result of me calling it earlier. And then I'm going to write that to-do to the response as part of my handle function. So we've glossed over read and write. I might just talk about those briefly in a moment, but you can assume that read is taking the response body and reading that as a suitable type, and write is taking our suitable type and writing that to the response body. In this case, both as JSON. So now if I fire that up, I should find that I actually passed that test because I'm writing this as part of my handler. Let's see. Yes, it does. So at this point, you're starting to get a bit of a feel for how we're building up these responses and how we're starting to extend our API. So you can see, for example, that the next thing we're going to want to do is to respond to a delete, and we're going to want to respond to a GET request to the API root with an empty array, which is obviously an empty to-do list. So I'm going to skip over a few of these and show you what it looks like a little bit later on. So now we've got our to-dos function, and we've added a few things. So we've added a to-dos clear function, which is going to delete the contents of our to-dos list. And that's obviously a delete on the root resource, which is a collection of to-dos, so we would expect that to clear them. And we've done something, again, pretty similar to what we had with to-dos add. We've got this do function, which it just calls to-dos clear. We've extended the methods that we handle here to support delete, and we've provided a function which is going to be called on do delete. We've also said that we're going to handle get properly on our to-dos resource. This is the to-do store list function, which is just an async function, which we call as normal. And then we have a handler for that, which calls that to-dos list function and writes our list of to-dos to the body. And in this case, we put that in as handle OK. And the reason that's handle OK is because we're handling the logical 200 case, which is just the correct response for a successful get. Okay, so if we were to run this one, we should see that we passed a few more tests. So we actually now we're responding successfully to deletes. We're responding to a get request with an empty array. We're also managed to, because we supported this post and this to-do create, we're passing these tests too, which is adding a new to-do to the list of to-dos. New to-dos have the correct status, and that's kind of handled by our domain model. New to-dos have a URL, which again we've handled in our domain model here. But we haven't. We're now passing, or failing to pass, more accurately, this test here. So when we actually try and get that URL, we should return a to-do. Well, we're not doing that, and we haven't actually implemented that resource at all. So let's see that we can actually. We're starting to do that here. So we've got now an extra resource. So this to-do resource, which is going to be our individual to-do. And we've mounted that. We've put that into our router at the /ID, which is the ID of the resource, or in this case the ID of a to-do. We've again included this. If you'll remember from earlier, our common configuration for machines. We've included that because we know that again that's just wanting to be some JSON representation supporting calls and this kind of thing. And we've said that this has some new options. What we do again there is, as we can see that we're passing some things, is that we'll go through and we'll take the same approach as we did with our to-dos list. We'll say, right, okay, we need to properly support get. We need to, in this case, we're going to need to support patch. So we're going to want to override some more things there. And we're going to want to be able to change things by supporting patch requests. Let's skip ahead a little and see what this actually looks like. So our to-dos request is as we had it, but we've extended our to-do resource quite a bit. We've said that we support delete on that, which we needed to pass a few tests, and we support patch. And you'll notice that we've got this this sort of fairly standard approach of the handling deletes, handling patches, and handling an OK case to actually get a to-do. So we'll be able to go back there and run our final implementation. And I'll just sort of show you as well that we're doing things like getting the ID from the root so that we can actually decide which to-do to get from our to-do store. Parsing that as a GUID, for example. And we'll be able to use that within our to-do method. And we should now see that if we run this, we're back to passing all of our tests. At least if I run them when the program started. Okay, that's great. So you can see how we can begin to build up more complex APIs by slowly implementing, a few more functions. So there's not a huge amount in here, and it's all sort of quite safe and quite tight. We're just building things up from lots of small functions and composing them. But that lets us do a lot of powerful things. Now, there's a lot of options that you can configure within Freya Machine, which we haven't done here. And a lot of those are quite interesting. So those are how we add safety to our handlers. So you'll notice that up here at the moment, I'm not really doing anything particularly interesting about saying, what happens if someone puts an ID in and that to-do doesn't exist? Well, obviously, at the moment, what we're saying is that the get handler will just assume that that to-do exists, and it will write it out. But actually, we know that we shouldn't be returning a 200 if that to-do didn't actually exist. So we can actually implement that. We could go in here and we could say, all right, I'm going to add some new configuration, which should be a function which returns true if my to-do exists. And it's actually very easy to implement that in isolation. So for example, I can just say, as my to-do get function returns a to-do option, I can say that it does exist if that option was sum. So my to-do exist function is just a Freya function of bool, which is what most of the decisions in a Freya machine are. You might ask why we'd actually want to do things like this. Why can't we just assume that all of these things return option, and then we'll be clever about deciding that if that's an option, we'll return the right case? Well, it actually turns out to be quite useful to be able to be a bit more explicit about different phases. So this to-do exists function at the moment is specialized purely for my to-do resource, but I could actually write a function if I wanted to, which looked at all of my resources. Which perhaps we cache the results of whether something actually exists or not, because fetching the actual resource is an expensive operation and we'd like to be a bit more efficient. If I wrote a function which cached that data, then I could share that function across multiple resources. So I can actually start to reuse those functions, and I can start to see all sorts of opportunities for writing a function or writing an API with a lot more reuse, making the logic that I write for each individual resource a bit smaller, but still getting this benefits of a much more functional approach to writing these, which is much more based on composition of small functions. So obviously I've had to skim over a few things to fit this into a sane kind of time. The code for this is actually up on GitHub, certainly on my GitHub account, which is github.com, and if you find collective, so that's probably going to be somewhere over here. We are going to see that. If you want to go and dive in and have a little bit more of a look at this code, you'll find that in my Lambda conf repository. All the slides for this and the code is there if you want to go and dig into that a little more deeply and actually see what I glossed over, which is quite a lot. And I'd encourage you as well to go and have a look at the Freya docs as well. I'm probably feeling quite guilty at the moment as we haven't written as many of those as I would love us to have done, but that's coming on quite well, and there's a lot of documentation which will show you even more about what's happening in there. There's a lot of features which I haven't covered here. There's some new levels of abstraction which we're working on, some discussions around things like hypermedia, or actually building a layer of abstraction above Web Machine to support things like hypermedia standards, where you'll have to do even less about the nuts and bolts of your responses, and you can concentrate much more on just defining what your resources are in a hypermedia sense. But for now, that's probably not a bad little sort of intro example. Hopefully that's been interesting to at least someone. And if anyone's got any questions, we'll see if we can answer those now. Ryan,
the Q&A section is open. No one seems to have submitted any questions yet. I've seen somebody mention on Twitter that they had no questions, that they were really enjoying and learning a lot from the talk. So thank you, Chet, for that comment. All
right. Well,
as someone who's been working on this, I can't ask any questions myself because you've I probably already know too much, and I thought you answered a lot of the questions that I was thinking of asking while you were talking. So that was very well done. Thank you, Andrew.
No problem. And hopefully, obviously, if people do want to ask any questions but don't get a chance now, we have we're moderate responsive on GitHub, and also we have our Gitter chat room. You'll often find at least one of us in the sort of F# Slack and that kind of thing too. So plus Twitter and all the usual kind of channels. So if there's anything which you want to play with or which you'd like to understand a bit more about, do just reach out to either of us, and we'll make sure your questions get answered. We're really keen to support anyone, particularly people who are planning on using Freya in a live setting, an industrial one if you like. And another note as well that the 1.0 of this is going to be coming out extremely shortly.
Excellent. And if you're, Andrew mentioned that he has the workshop code available. There's also Freya.examples under the Freya FS organization. So you can see the to-do backend implemented there, as well as a static file server, I believe, is implemented there.
Yeah.
If you do want to see some examples, there are a few there.
Just a simple static file server. Obviously, that's quite a nice little example, which is to show that it's this machine model isn't just sort of only suited to writing APIs. It's actually quite a good abstraction for writing all kinds of things. And yeah, there's a simple little static file server there which will do sort of nice content negotiation and that kind of thing, based on sort of dynamic directories of content. And that's quite a nice little demonstration of an alternative way to use something like this.
Excellent. Well, thank you, Andrew. Thank you for the time. Thank you for doing an excellent presentation on Freya today. For those of you who are regulars with Community for F#, we do have another event coming up with Ricardo Terrell. He will be presenting on another web topic related to real-time web with SignalR and F#. So stay tuned for that. That will be coming in mid-June. So we're excited to have him. And again, thank you, Andrew. Lots of content for web stuff. If you have any suggestions on additional topics you would like to see presented, or you would like to present yourself, please reach out to at C4F# on Twitter, or you can find the Google Plus page for Community for F# and leave some recommendations or requests to present there. You can also contact me directly if you like, and you can find my email all over the place. Probably the best place to look would be on my GitHub page, github.com/panesofglass. And that's it. Thank you all for joining, and thank you, Andrew, once again for presenting. The recording should be available soon.